In this video, we're going to explore some of the different styles of micrometer that are available to you. Now, these different styles will help you with features that your standard outside diameter micrometer either is not the best gauge for the job, or physically just can't do it. There's a lot of features that a standard OD mic can't wrap its anvils around. For example, internal grooves, inside diameters, flanges where there's interference with another feature. So we have some of these other tools available to us that maintain that micrometer accuracy, that micrometer rigidness, and allow us to inspect these other features. Now, there's a wide variety of micrometers available in many different styles for many different applications. And typically they're developed when a product is being made in high volume, and somebody thinks, well, we're going to need something better than what we have. Let's design something we can use specifically for this application. And that's how a lot of these micrometers came to be. So we're going to go over some of the more popular, more common styles, but remember, if you need something very specific for your application, take a look at some gauge manufacturer catalogs, and you might be surprised to find that there's something available for what you need already. So, let's go over some of the common styles we're going to go over. We'll talk about blade micrometers, disc micrometers, and pin micrometers, and those are all pretty much modified outside diameter micrometers with a different anvil shape than just your typical closing OD mic anvil. We'll talk about a multi-anvil micrometer, which allows you to change the anvils, interchange anvils for different applications. A depth micrometer, which I have here, help you measure the distances down from one face to the next face. A groove micrometer will help you measure inside and outside grooves. And then we have interchangeable anvil tips, like this. This is an anvil tip for a pitch mic. So sometimes you can get some of these different anvils just by changing the tip of the OD mic and get some of these applications. So we're going to start off with the disc micrometer. It's fairly straightforward. You basically, instead of a standard OD mic anvil, you have a larger flange, and that will help you, get into some tricky tight tolerance situations. For example, I have this part here with some flanges, and I really wouldn't be able to get my OD mic on the flanges. Go to the other camera. I wouldn't be able to get my OD mic on any of these flanges, but because these extend a little bit outside the envelope of the micrometer, I can now take a thickness reading with this, and we can take our reading directly of 0.203 and a half roughly. So that's one application for a flange. Some other applications, sometimes you just have a small part, and yes, your OD mic could get on it, but in reality you want a sort of a larger, maybe you're having trouble centering it, so you want to grab a larger flange just because you're having trouble centering it, and you want to still be able to get anywhere on it. That's another application I've used sometimes. But I mean, it's pretty straightforward. It's just like an outside mic where you operate it the same way, and it can measure many of the same features and give you a little bit more when you have sort of a small registration point. I'm not sure I've got a handy part where there's a small registration, but sometimes a flange like this, it may just not have a lot of surface area to grab onto, so you can use your OD, your disc mic to get a little bit better registration than with a standard mic. Actually, maybe this part might be a good example. If I were going to measure this thickness with my OD mic, it might get a little bit challenging to avoid the sidewalls. I can still get a pretty decent registration with my OD mic here. Oh man, there's a bunch of stuff that the camera's trying to focus on. Let me move all this out of the camera view. So we can, we can get our registration there, but it may be easier get a larger anvil on it. And I can more easily clear the body of the micrometer. So again, maybe not the best example of a part. I don't have a great example to work with, but pretty much how you're going to use it. I do want to point out there's this anvil, this moving anvil, is not rotating. So it's remaining stationary because there's a groove here which has a little dust in it. There we go. There's a groove here that keeps the anvil from rotating. So this is a style of micrometer with a fixed rotation. So just be aware, it doesn't really matter for your application. It's a little bit more complicated of a mechanism, but a lot of these anvils are going to work that way because if it rotates, sometimes you don't get proper alignment. So let's go back to the summary. So some strengths, right? Outside flanges and part thicknesses. Some weaknesses. Sometimes because you're relying on the outside of the disc so much and you're not grabbing the middle of the disc with your part because of the application, the edges are going to wear a little bit faster. So yes, you may close this on 0, and because the middles are not being used a lot, it still zeros accurately, but the flanges have worn and there'll be a gap. So you'll need to hold it up to the light when you zero it and check for any wear where you're actually using it. Another problem is sometimes you can really, because the edges get worn a lot, they might get damaged. You might have slid it off your part and caused a little bit of damage over time and caused it to bend. And now one of these anvils is out of alignment with the other one. So when you close it, right, you get a reading. Maybe you zero it off of that. But when you go to take it opens up and you measure a part, it's no longer accurate. So again, that's another time to hold it up to the light and look for a misalignment. And then your last, your last couple of bullet points here: anvil tip interference during measurement and radius or taper. Because of these tapered, you don't really have a straight flange anymore. You have a little bit of a taper here, and sometimes these can be pretty severe. And this is for strength. But sometimes these flanges will interfere when you try to get inside of a groove, and you just won't realize it. And it might be hitting on the top here. So be aware of that. Internal radiuses, sometimes when you're a lathe process may leave a little radius on here, and you may end up putting your anvil on it without realizing. So you'll have to slide away just a tiny bit from the inside, just slide out a little bit and take your measurements so you're not grabbing onto a radius that you can't see. And then that last one, for taper, sometimes a longer part may be tapered, and so it's just like an OD mic, except because you have a larger anvil, it may pick up the taper in different places than your OD mic would. So it might be loose because you have such a large anvil that's not making contact on a larger surface. So with a smaller anvil, that taper effect is going to have kind of a less of an effect. Because you have a smaller anvil, the percentage of the anvil that's making contact will be larger when you're working with a standard OD mic. But with a typical flange mic, as you're going around, and there may be more of the part, or more of the anvil is not making contact, so you can wiggle it around when there's taper involved. So again, I think it's a good tool to have for certain applications that your OD mic is not good for, and it's a very common gauge you'll find in businesses and shops. Next up, we're going to talk about the blade micrometer, and I do not have a blade micrometer with me for this video right now. If I can get my hands on one, I'll record a video demonstrating it. But for right now, we're just going to talk about it, and it's basically this, same idea as a disc mic, but instead of having a large disc, you get a very thin blade to grab onto. And again, the point of that is to clear features where a standard OD mic couldn't get into. So if we take a look at this groove part I have here, you can imagine my OD mic anvil is just too big to get in those grooves. But if I had a thin blade, I would be able to get that diameter, I would be able to get the diameter across it if I had a thin blade that would fit into the grooves. So that is one of the more common applications. And another application might just be you've got a really small registration space, and with your round Anvil micrometer, that really small registration space, it only makes contact, partway on the circle. You can't get to the middle. But with a blade, you can get more surface area because the blade is just a thin strip, but it's longer than your small diameter. So when you go to register on a part, instead of registering on the end, you're kind of registering on the middle of the blade and getting more surface area. So that's another application, besides thin grooves. You can use it for times when you have small registration with an OD mic, but you can get bigger registration with the blade mic. Some weaknesses you need to be aware of for blades is anvil damage. First and foremost, because there's such a small contact area, it can be very easy to damage those anvils if you crank down a little too hard with your thimble, and maybe you nick the parts in and out a lot when you're using them. They're so small and thin, they can go out of alignment. So yeah, again, hold them up to the light, look for damage, and look for perpendicular alignment. You're calibrating on a small contact area, so you really got to be careful with your whatever block you're using. Make sure that it's straight and it's not twisted. And then it has the same issues as the disc with anvil tip interference. If you take a look at this picture, you have kind of a thin blade here, but then at this part of the body you do have a kind of a tapered, reinforced section that could interfere before you get to the main spindle body. So both of them will have kind of a tapered flange fillet here that you could interfere with when you're trying to get inside of the groove. So watch for those. If you don't see it happen, you'll just feel it stop and you'll think, oh, I'm making contact. But in fact, the blades will have not made contact yet, and you will have made contact up here at the tapered section. And of course, you need to avoid radius and taper. Taper won't be so much of an issue with a blade, but it will be kind of hard to grab onto the parts that have a little bit of taper. They'll be kind of sliding and twisting a lot because there's very little contact area. So you want to be careful, make sure you have good registration if you are using a blade on something with a taper. Again, this is another non-rotating spindle as well, because if those flat sections are not lined, they're kind of useless. So they will always be non-rotating and make straight alignment when you close them. Next up, a pin micrometer. That's another micrometer I don't have with me right now, but some strengths. If you imagine, it's basically just a very small anvil. So instead of your typical OD mic, you just have a very small diameter or even a very tiny point. And again, you're just trying to get into tighter diameters with small clearances. Sometimes you'll have thick but shallow flanges that you can get into with those that you can't get in with your OD mic. Weakness, again, contact area. You have a very small contact area and you're applying a lot of force when you close down with your micrometer. And if you don't adjust the force you use with a standard OD mic and a very small Anvil pin mic, you could damage your micrometer that way. So look for that misalignment when holding up to the light. Look for that damage. Look out for the interference. It's just the same as the other ones. You just have to watch out for making sure you're making contact where the anvils are and not on these tapered, reinforced sections of the body. And then, with this one and even with the blade, I would say you really have an easy chance to slip off the part when you're trying to wrap your really tiny anvils around a diameter. It can be very hard to do that with a small contact area. It may slip off a lot, so you have to be a little more careful, a little more methodical, and have a steady hand when you're doing these measurements, because it is frustrating when it's constantly sliding off and you have such a small anvil contact area. It may be a good time to break out a micrometer clamp and clamp down on your micrometer so that you can just hold your part and close it rather than having to hold everything. And as another situation, sliding the part on and off to take your reading like we do with a standard OD mic, it may be a little bit harder. You can certainly lock it down, but in my experience, it's a little bit easier to just read it while it's there, because it may have a tendency to move as you try to slide it off because it's so small of an anvil area. And there's a lot of force on those points and it's not spread out, so when you're sliding it off, it may bump the measurement one way or another. So just keep that in mind. If you're going to be doing that, try reading it there if you can, or be very careful when you slide it off. All right. Now we're going to move on to a multi-anvil micrometer. So those first three micrometers were all pretty much the same OD mics, modifications of OD mics. But this is a heavily modified OD mic. And with this micrometer, you basically have a standard OD mic moving spindle anvil. There's no modifications to this side, but the fixed side that you normally use, you now have a clamp here, and you can clamp in a flat end or a pin, and you can get different anvil registrations with these different, either a pin or a flat face, and that will help you in certain situations. Sometimes you want a round surface, sometimes you want a flat surface. And I don't actually have a multi-anvil micrometer. I have a tube micrometer here to show you. And I can use, I can show this to you the same way I would use a multi-anvil. I just don't have that flat interchangeable piece. All I've got is kind of the round end, and it's fixed. It doesn't come in and out, but we can still talk about it and demonstrate it as if it were a multi-anvil. So, what are some strengths with this one? Well, this is a great tool for measuring symmetry when you have, this. Let me bring up the pointer so I don't have to keep fighting it. There we go. So, wait, hold on. Did I hide it? I did hide it. All right, visible. So when you're using the The multi-anvil, what's great about it is you can take apart, something with round features, and maybe it's supposed to be symmetric, and you can put your anvils in and clamp down and go rotate the part and clamp down, rotate the part, clamp down, and by checking if it's centered relative to the outside, you're verifying that it's symmetric relative to the outside. And there's a lot of applications for that in manufacturing. You want inside features centered and symmetric relative to outside features. So you could do that with a multi-anvil very easily. So you can do concentricity or runout checks. And in fact, concentricity is a tricky subject, which I talk about in the GD&T videos. But basically, in some applications of concentricity, you will do a runout check. And this is a very particular application where you can do a runout check between diameters. So I'll demonstrate that in a minute here. In many situations, another strength is because you're checking symmetry, calibration is not required. Because what you'll be doing is you'll be closing this anvil on a feature, looking at the measurement, and it really doesn't matter exactly what that measurement is, but when you check all around, you're looking for symmetry. You're looking for TIR, essentially, total indicator readings. So it's not an indicator, but you can use it that way. So why don't I demonstrate how this works. So again, I have a tube micrometer, but a multi-anvil micrometer would have a pin, and it's literally pretty much you can either clamp the pins that come with it, or you can use pin gauge sets and get a pin that you need and clamp that one on there. But the key point is I'm going to have a round anvil here instead of a flat. And because of that, if I wanted to know how concentric is this inside diameter to this outside diameter, well, I'll just clamp onto it this way and then rotate at 4 places. So my reading is 0.247, if I read that right. Let me just verify that with a micrometer, with a caliper. Oh, 0.253, I think I read it wrong. All right. Actually, I think I got it right. I think they're just registering differently. So, yeah, we'll call this 0.246 on the scale here, on the vernier scale. And then I'm just going to rotate to another point, and ooh, yeah, that's why I was getting some different readings. They actually are not very concentric. So now I'm at 0.250 and about 0.2. And go around to another location, about 0.252 and a half, and go to another rotation, and about 0.247 again. So all I do is I unclamp it, rotate it around, and clamp it down again, and take my reading. So because I'm getting a difference in readings, I've got a concentricity problem, or sorry, I have a runout problem. And this is actually a good part to use as an example, because it might be difficult to verify the inside diameter and the outside diameter concentric with a surface plate measurement. We would normally do a runout check with a surface plate measurement. It's one of the easier ways to do it, but it's actually going to be harder because it's going to be harder for me to, we're going to have to set up our outside diameter on a V block, and because it's so imbalanced, it's going to be very hard to keep it balanced. We could also stick a pin in, and that might be possible if I had the pin size that goes in here. Let's see what pin size goes in there. You know, if I had about a 753 or 752, whatever size ends up going in there, I might be able to get a pin in there and clamp the pin on the V-block, but even then, it's such a small registration. That's a very difficult way to check if it's running out, again, because it'll be flopping around on the pin. So using a multi-anvil, or in this case, a tube micrometer, you know, I can get that runout check very easily. And using the round anvil again, I could measure hole locations. You know, if we took a look at the angle block drawing PM-02, and I'm supposed to be 0.5 from the bottom on this hole here, we could do that with a. We could find the location by measuring the distance to the bottom edge and then adding the radius of the hole. So let's quickly do that. You can see I've got a nice registration on the surface, on the outside surface, and I have a nice registration on the inside. It kind of self-centers when I rock it around, and it allows me to find the part edge. It self-centers. It kind of registers itself. So I'm at 0.3 and about 5/10. 6/10, 0.3 and 6/10. So let's write down that in our calculator. We got 0.3 and 6/10. And then we're going to add the size of the hole, which I will do with a caliper in this case, just to save a little time. So we'll say 0.396 is where it seemed to register. So we'll find out that radius. And I'm at 0.4986. And our print said to be at 0.5. So that's a very nice way to use a micrometer to get a hole location, registering one end on a round surface, the other end on a flat surface, using a multi-anvil or a tube micrometer. Now that flat anvil that I don't have just to demonstrate with you right now, but that might work if you had a square feature in here instead of round features. Maybe you have a slot, and that might work well for registering two flat surfaces on a slot. For example, like this slot here. You know, I could get my multi-anvil and get the outside over here, and get the interchangeable anvil on this side, and a flat anvil would just help me register a little bit better. But even the round kind of self-centers as well. So, most of the applications when I use a multi-anvil, I want that round anvil because it gives me a new option that I really didn't have before. So I think that's one of its more common uses, to verify round to flat features, or to verify runouts. Another one we could do, I'm trying to find a good part to work with out of what I have. Sometimes, I said, we were doing a runout check with this, but it's also a symmetry check. It's telling you how centered the inside is relative to the outside. But these are two rounds features. Well, you could do it if I know for a fact this hole is not supposed to be centered, but if it were supposed to be centered, I could do it from this edge. Actually, yeah, I could do it from this edge and this edge and tell me how far off center it is. But unfortunately, this hole wasn't designed to do that. But if you imagine, I'll do it with a caliper, but you could do the same thing with your multi-anvil, is grab that outside edge and that edge and that hole edge, and then grab that outside edge and that hole edge, and look for the difference. Now this is designed to be off center. I wish I had a kind of a good part that wasn't round to do that with, but unfortunately I don't have that right now. So just keep that in mind. Symmetry is one of the shortcuts in metrology that will really help you. Let's talk about couple of weaknesses. The calibration does go out every time you change this anvil here. Your calibration can change. Now, theoretically, the anvil is being registered on this flat surface right here, and hopefully it's flat and perpendicular relative to the spindle, so that when you do change this, the calibration doesn't change. But in practice, I've seen it move 5,000 sometimes at the most. And so you do need to grab your calibration tool and adjust your thimble if you're going to be doing a direct reading. If you're going to be doing a symmetry check and you're just looking for the difference, like we did with this part, we're just looking for the difference around, then you actually don't need to calibrate the gauge. I shouldn't say that, but you're not measuring a distance from zero. You're just measuring relative to its current calibration state. So whenever I do a quick symmetry check, I really don't need to verify the zero, and that helps because you're changing the anvils a lot sometimes. Aligning the mic straight and finding the smallest point, that can be hard as well, because sometimes you've got a long anvil sticking out. You don't have these these anvils are much longer, thinner and skinnier than your typical anvil, and sometimes they'll be out of alignment, and it can be hard to kind of twist this thing because you're working with this big anvil sticking out. You've got this tiny anvil trying to make contact, and it can be hard to align the difference in size. So just be careful and try to repeat it. When you can get good repeatable checks, then you know you're okay. And then remember the wear pattern of this anvil, multi-anvil style, it's going to wear differently than a typical OD mic. So just be aware of that. Your interchangeable anvils will get different wear patterns because they move and they rotate. They don't make contact in the same point all the time. So just be aware of that. Keep a close eye if you're using these a lot and you're checking direct readings. You can still grab a set of Joe blocks and check the stroke just like we do with OD mics. So we did this as an example, and we did it with the tube mic, and this is actually it's a tube mic for this reason. You're checking how thick a tube is, or a wall thickness is. And this would be an example, a written down example of trying to measure the runout of the ID, which we don't know the diameter, and it doesn't really matter, to the OD. The OD is datum A. And so we had our micrometer registered on the outside at 4 places and the inside at 4 places, and any difference in thickness is going to translate to a runout error. So this works. It's not like your typical surface plate inspection, but runout is basically just the difference from one surface to another. And so you look at all your readings. You look for the lowest reading, 0.124, the highest reading, 0.126, and the difference is equal to your measured runout. So now you do need to be aware. I say this is okay to do, but there will be some situations that might throw you off, which I'm gonna draw out for you. All right, this is kind of assuming you have a good process in place and you're going to be avoiding some issues I'm going to draw out for you. But when we talk about runout, which I go into great depth on in the GD&T video, the surface plate videos, you have a few situations where you could have a really good symmetric shape outside diameter, and your inside diameter could either be off-center or oval-shaped, in which case when you do your checks, you're going to get really vastly different readings. So this is a situation where you're going to see a lot of problems. You're going to see a lot of issues. this may not necessarily be a runout issue. This looks like a feature fabrication issue where the size is wrong, the shape is wrong, and the position is wrong. Everything's wrong. You could have another situation where the outside diameter is oval shaped, but your inside diameter is actually relatively good relative to center and to outside. So you'll put your anvils on at multiple locations, and when you do this one, you're still going to see a lot of TIR, right? Or not TIR, but you're going to see a big difference in your anvil readings on the long ends relative to the short thicknesses. So short thickness here, large thickness here. That would show up on an indicator as well. As if you set up a surface plate inspection, you would see the same thing. So what this is really doing is verifying you have good parts, and if you don't have good parts, hey, look at that. If you don't have good parts, you'll see it as well. And I use this to get my final reading. Sometimes, as I said, it's going to be hard to do this check on a surface plate. It's just going to be tricky, and I have a good hand tool to do it with instead. And I feel like I'll get a better reading than trying to set up a complicated fixture. I could take it to a CMM. That might be ultimately the best situation. But be aware. I like to always tell you guys, your part is not perfect. Your part has errors that you're not aware of, and you're looking for them. And sometimes it will manifest itself in different ways, in position errors and shape errors. And how that affects your reading can sometimes be a problem. I'll show you a couple more situations. Actually, I just thought of, what if you needed two diameters and they're both ovals, and you go to do your reading, you're not going to see any TIR, right? So this might be a situation where this check doesn't work. You're not going to see any TIR, but you're obviously no longer a diameter. So what does this mean? They are running out the same. The runout check passes. But are there any diameter requirements? Are there any form error requirements that this will not find? This will not reveal any issues. So you'll still be measuring the diameters with other gauges. This is only doing the runout. This is only doing the runout portion. But something like this wouldn't show up. It would show up as being equal all around. All right, let us move on to the depth micrometer. Now this is a very popular gauge. Where did I put my depth? Oh, here's my depth micrometer. A very popular gauge is something you should be using all the time because it measures the difference between plane levels, which is very common on parts. You have different levels of parts relative to the outside, and in many cases you can't do it with an OD mic, so you'll have to use this mic. What's nice about these is they have multiple interchanging anvils. You can see there. I don't have them with me for this video, and I'm not going to need them. But you can basically unscrew the cap and switch out the anvils. So a typical OD mic might go 0 to 3 inches, 0 to 6 inches, and I've even seen 0 to 12 inches, where you just keep changing out those anvils and you get 1 inch of travel, but the anvil is now, an inch longer, an inch shorter, depending on what you changed out. And this is a great replacement for the caliper depth bar because you get an accuracy out of a micrometer, relative than your caliper depth bar. So this is a great replacement for that when you have a precision depth that you need. Now, a few weaknesses. Again, every time you change the anvil, it's possible the calibration is changing, when these anvils get longer and longer, they tend to get bent, damaged, warped. So that may change your calibration. Now, theoretically, in perfect condition, they can interchange and not affect your calibration. But I do like to grab another block, and if I have my 4-inch anvil in there, I'll check it against the 4-inch block. If I have my 2-inch anvil, I'll check it against a 2-inch block just to be certain that I'm getting the accuracy I need. So that goes into weakness 2, maintaining the long angle straightness. You do need to watch out for internal radiuses. I'll demonstrate that. Tapers, drill points, fixed anvil clearance and perpendicularity. Sometimes you'll be rubbing on a sidewall as you extending this anvil inside, and it's no longer perpendicular. And then your touch and ratchet. Some of these have ratchet. Some of these have that ratchet feedback that will stop you, and that can be really tricky to use when it's inside of a feature and you can't see it. You can't see what it's rubbing on. You can't see if it's hitting the bottom or radius, so that may not be so accurate. And I've seen a lot of people make the mistake of, the ratchet feedback kicked in while it was rubbing on something, and it never actually made it all the way down to the depth it was trying to reach. So let's demonstrate. First thing I'll do is demonstrate the interchangeable nature. You can just pop off the cap, pull out your anvil, and slide it back in, and put the cap back on, and you're ready to go. How we calibrate and how we check calibration is we'll need a clean calibrated surface plate, and you will just retract it all the way and bring it into contact with the surface plate. Oops, I bumped it. And what have we got? Hold on a second. There we go. So we've got a little bit less than 0. Let me check one more time. And just about a tenth less than 0. And we've got, oh, you know what? This one doesn't have that micrometer adjustment. So, many of these do have the ability to adjust the sleeve with a typical micrometer wrench, or probably more like this style. But actually, it appears this one doesn't. So what I'm going to do, I take a look and I say, yeah, it's about 1/10 off. And I'll just remember that as I'm taking my readings. So it's minus 1/10, which means everything I'll do, I'll have to add 1/10. But normally I would try to adjust this in. It could be you just need to apply less pressure or more pressure with this style. I'm not too familiar with this one. I was able to borrow it for this video, but overall it's in pretty good condition other than this little 0 issue. So how we can measure, if we wanted to measure from this face to this step height, all we do is kind of slide it on and just rotate it down until it makes contact. And I'm not using the ratchet, I'm just going by feel. Okay, and we'll take our reading. You'll notice the numbers are kind of opposite. Trying to get the camera to focus. It doesn't want to. There we go. You'll notice that the numbers go backwards. If you can't see it on, man, it doesn't look so good on the screen there. take a look at the second camera feed. You'll see that it starts off at 9 on this side and moves down 87654. So this Anvil is moving kind of opposite the way, well, not opposite the way outside diameters, outside mics work, but in fact it's recording the opposite. It's not recording the size of something, it's recording how far it moved. So 0 with an outside diameter mic, right, it's normally, you know, some distance over here, but we're not doing it that way, so the numbers are backwards. So we're looking at just less than 0.4. We're looking at about 0.375 plus 17, 0.385, 0.389. So we're looking at 0.389. And not that drawing. We take a look at our drawing. It's right here. To the second step, we're supposed to be 0.610 from the backside. So we'll do a little shop math. It's 1 inch thick, and we're going to subtract 0.389, and we get 0.611. Hope you can see that. So I used 1 inch thick without verifying it. Let me verify it. Actually, it's about 0.997. So we'll redo that calculation. 0.997 minus 0.389, 0.608. So we're still in tolerance to our RPM02 reading. We have plus or minus 5. So you may need to use shop math depending on how your print is. If the print referenced it directly off of the top surface, then we would be able to just do a direct reading. But in this case, we had to do a shop math. So, you know, doing steps is one way to get this done. Another way is we can measure the counterbore depth on the internal feature. And we're going to need to try to avoid rubbing on the sidewall as well as hitting the radius that's left over. So I'm going to braze this up again, and so I'm going to push it against the sidewall and then come out just a slight bit, so I'm avoiding the sidewall, avoiding the radius. And then just go by feel. So now, let's see. Oops. I'm reading about 378. Take a look at our print. PM02 print. And we're supposed to be depth of 0.375. So we're doing all right. 378, 375 plus or minus 5. So we're doing all right. And you know, that's a couple of typical examples of measuring to an inside feature or measuring a flange depth. I could do the same thing with this depth, you know, use a depth mic all day trying to get these features. And that's about it. If you're getting a large mic, as I said, remember to maybe check your full stroke. I probably should have done that at the beginning. Let's check our full 1 inch stroke, just to make sure we're getting good travel. And I've got a little bit of difference. I had about 0.0. I had 1/10 of error minus at the beginning. At the end of stroke, I probably have about 0.2 of error. Sorry that the camera's not focusing for you guys. I have a little bit more error, so it's a good point to talk about. Depth mics will not typically have the same accuracy as an OD mic because you're not registering on two anvils. You're only, well, you are registering on two anvils. You're registering on your anvil up here and here, but they're not closing on each other, so that typically introduces a little bit more error. And when you take a look at the manufacturing specs, you'll see that's reflected in their catalog. And the more you travel, the more error you're going to get. So even when you get the bigger anvils in, you're going to get a little bit more error, and your manufacturer will typically write that in some fashion. You typically will add a tenth or two as the anvils get bigger and bigger. So just be aware of that. Take a look at what your actual anvil, what your actual part is set for, is rated for by the manufacturer. All right, before we move on to groove mics, I'm going to stop the video, take a quick break, and we'll move on in just a moment. So thank you for watching, and stay tuned for the next one.